Stanford University.
Okay, can everyone hear me? Okay, sorry for the delay. I had a bit of technical difficulty. Today was the first time I was trying to use my new Touch Bar MacBook Pro for presenting, and none of the adapters are working. So I had to switch laptops at the last minute. So thanks. Sorry about that. So today is lecture 10. We're talking about recurrent neural networks. So as usual, a couple administrative notes. So we're working hard on assignment 1 grading. Those grades will probably be out sometime later today. Hopefully they can get out before the A2 deadline. That's what I'm hoping for. On a related note, assignment 2 is due today at 11:59 p.m. So who's done with that already? About half you guys. So I remember I did warn you when the assignment went out that it was quite long and to start early. So you were warned about that. But hopefully you guys have some late days left. Also, as another reminder, the midterm will be in class on Tuesday. If you kind of look around the lecture hall, there are not enough seats in this room to seat all the enrolled students in the class. So we'll actually be having the midterm in several other lecture halls across campus. And we'll be sending out some more details on exactly where to go in the next couple of days. So another bit of announcement. We've been working on this sort of fun bit of extra credit thing for you to play with that we're calling the training game. So this is this cool browser-based experience where you can go in and interactively train neural networks and tweak the hyperparameters during training. And this should be a really cool interactive way for you to practice some of these hyperparameter tuning skills that we've been talking about the last couple of lectures. So this is not required. But this, I think, will be a really useful experience to gain a little bit more intuition into how some of these hyperparameters work for different types of data sets in practice. So we're still working on getting all the bugs worked out of this setup. And we'll probably send out some more instructions on exactly how this will work in the next couple of days. But again, not required, but please do check it out. I think it'll be really fun and a really cool thing for you to play with. And we'll give you a bit of extra credit if you if you end up working with this and doing a couple of runs of it. So we'll again send out some more details about this soon once we get all the bugs worked out. So as a reminder, last time we were talking about CNN architectures. We kind of walked through the timeline of some of the various winners of the ImageNet classification challenge. Kind of the breakthrough result, as we saw, was the AlexNet architecture in 2012, which was a 9-layer convolutional network. It did amazingly well, and it sort of kickstarted this whole deep learning revolution in computer vision and kind of brought a lot of these models into the mainstream. Then we skip ahead a couple years and saw that in 2014 ImageNet Challenge, we had these two really interesting models, VGG and GoogleNet, which were much deeper. So VGG was, they had a 16 and a 19-layer model, and GoogleNet was, I believe, a 22-layer model. Although one thing that is kind of interesting about these models is that the 2014 ImageNet Challenge was right before batch normalization was invented. So at this time, before the invention of batch normalization, training these relatively deep models of roughly 20 layers was very challenging. So in fact, both of these two models had to resort to a little bit of hackery in order to get their deep models to converge. So for VGG, they have these 16 and 19-layer models, but actually they first trained an 11-layer model because that was what they could get to converge, and then added some extra random layers in the middle, and then continued training to actually train these 16 and 19-layer models. So managing this training process was very challenging in 2014 before the invention of batch normalization. Similarly, for GoogleNet, we saw that GoogleNet had these auxiliary classifiers that were stuck into lower layers of the network. And these were not really needed for the class to get good classification performance. This was just sort of a way to cause extra gradient to be injected directly into the lower layers of the network. This again was before the invention of batch normalization. And now once you have these networks with batch normalization, then you no longer need some of these slightly ugly hacks in order to get these deeper models to converge. Then we also saw in 2015, in the 2015 ImageNet Challenge was this really cool model called ResNet, these residual networks, that now have these shortcut connections that actually have these little residual blocks where we're going to take our input, pass it through the residual blocks, and then add that output then add our input to the block to the output from these convolutional layers. This is kind of a funny architecture, but it actually has two really nice properties. One is that if we just set all the weights in this residual block to 0, then this block is computing the identity. So in some way, it's relatively easy for this model to learn not to use the layers that it doesn't need. In addition, it kind of adds this interpretation to L2 regularization in the context of these neural networks. Because once you put L2 regularization, remember, on the weights of your network, that's going to drive all the parameters towards 0. And in maybe your standard convolutional architectures, driving towards 0 maybe doesn't make sense. But in the context of a residual network, if you drive all the parameters towards 0, that's kind of encouraging the model to not use layers that it doesn't need, because it will just drive the residual blocks towards the identity where they're not needed for classification. The other really useful property of these residual networks has to do with the gradient flow in the backward pass. If you remember what happens at these addition gates in the backward pass, when upstream gradient is coming in through an addition gate, then it will split and fork along these two different paths. So then when upstream gradient comes in, it'll take one path through these convolutional blocks, but it will also have a direct connection of the gradient through this residual connection. So then when you imagine stacking many of these residual blocks up on top of each other, and our network ends up with potentially hundreds of layers, then these residual connections give a sort of gradient superhighway for gradients to flow backward through the entire network. And this allows it to train much easier and much faster, and actually allows these things to converge reasonably well, even when the model is potentially hundreds of layers deep. And this idea of managing gradient flow in your models is actually super important everywhere in machine learning and super prevalent in recurrent networks as well. So we'll definitely revisit this idea of gradient flow later in today's lecture. So then we kind of also saw a couple other more exotic, more recent CNN architectures last time, including DenseNet and FractalNet. And once you think about these architectures in terms of gradient flow, they make a little bit more sense. These things like DenseNet and FractalNet are adding these additional shortcut or identity connections inside the model. And if you think about what happens in the backward pass for these models, these additional funny topologies are basically providing direct paths for gradients to flow from the loss at the end of the network more easily into all the different layers of the network. So I think that, again, this idea of managing gradient flow properly in your CNN architectures is something that we've really seen a lot more in the last couple of years, and we'll probably see more moving forward as more exotic architectures are invented. We also saw this kind of nice plotting performance of like the number of flops versus the number of parameters versus the runtime of these various models, and there's some interesting characteristics that you can dive in and see from this plot. One idea is that VGG and AlexNet have a huge number of parameters, and these parameters actually come almost entirely from the fully connected layers of the models. So AlexNet has something like roughly 62 million parameters, and if you look at that last fully connected layer, the final fully connected layer in AlexNet is going from an activation volume of 6 by 6 by 256 into this fully connected vector of 496. So if you imagine what the weight matrix needs to look like at that layer, that weight matrix is gigantic. Its number of entries is 6 by 6, 6 times 6 times 256 times 496. And if you multiply that out, you see that that single layer has 38 million parameters. So more than half of the parameters of the entire AlexNet model are just sitting in that last fully connected layer. And if you add up all the parameters in just the fully connected layers of AlexNet, including these other final fully connected layers, you see something like 59 of the 62 million parameters in AlexNet are sitting in these fully connected layers. So then when we move to other architectures like GoogleNet and ResNets, they do away with a lot of these large fully connected layers in favor of global average pooling at the end of the network. And this allows these networks to really cut these nicer architectures to really cut down the parameter count in these architectures. So that was kind of our brief recap of the CNN architectures that we saw last lecture. And then today we're going to move to one of my favorite topics to talk about, which is recurrent neural networks. So far in this class, we've seen what I like to think of as kind of a vanilla feed-forward network. All of our network architectures have this flavor where we receive some input, and that input is a fixed size object, like an image or a vector. That input is fed through some set of hidden layers and produces a single output. Like a set of classification scores over a set of categories. But in some contexts in machine learning, we want to have more flexibility in the types of data that our models can process. So once we move to this idea of recurrent neural networks, we have a lot more opportunities to play around with the types of input and output data that our networks can handle. So once we have recurrent neural networks, we can do what we call these one-to-many models, or where maybe our input is some object of fixed size, like an image, but now our output is a sequence of variable length, such as a caption, where different captions might have different numbers of words, so our output needs to be variable in length. We also might have many-to-one models, where our input could be variably sized, This might be something like a piece of text, and we want to say what is the sentiment of that text, whether it's positive or negative in sentiment. Or in a computer vision context, you might imagine taking as input a video, and that video might have a variable number of frames. And now we want to read this entire video of potentially variable length, and then at the end make a classification decision about maybe what kind of activity or action is going on in that video. We might also have problems where we want both the input and the output to be variable in length. We might see something like this in machine translation, where our input is some maybe sentence in English, which could have a variable length, and our output is maybe some sentence in French, which also could have a variable length. And crucially, the length of the English sentence might be different from the length of the French sentence. So we need some models that have the capacity to accept both variable length sequences on the input and on the output. Finally, we might also consider problems where our input is variably length, like something like a video sequence with a variable number of frames. And now we want to make a decision for each element of that input sequence. So in the context of videos, that might be making some classification decision along every frame of the video. And recurrent neural networks are this kind of general paradigm for handling variably sized sequence data that allow us to pretty naturally capture all of these different types of setups in our models. So recurrent neural networks are actually important, even for some problems that have a fixed size input and a fixed size output, recurrent neural networks can still be pretty useful. So in this example, we might want to do, for example, sequential processing of our input. So here, we're receiving a fixed size input, like an image, and we want to make a classification decision about like what number is being shown in this image. But now, rather than just doing a single feed-forward pass and making the decision all at once, this network is actually looking around the image and taking various glimpses of different parts of the image. And then after making some series of glimpses, then it makes its final decision as to what kind of number is present. So here, we had here, even though our input and outputs, our input was an image, and our output was a classification decision, even in this context, this idea of being able to handle variably length processing with recurrent neural networks can lead to some really interesting types of models. There's a really cool paper that I like that applied the same type of idea to generating new images, where now we want the model to synthesize brand new images that look kind of like the images it saw in training. And we can use a recurrent neural network architecture to actually paint these output images sort of one piece at a time in the output. So you can see that even though our output is this fixed-sized image, we can have these models that are working over time to compute parts of the output one at a time sequentially. And we can use recurrent neural networks for that type of setup as well. So after this sort of cool pitch about all these cool things that RNNs can do, you might wonder, like, what exactly are these things? So in general, a recurrent neural network has this little recurrent core cell, and it will take some input x, feed that input into the RNN, and that RNN has some internal hidden state. And that internal hidden state will be updated every time that the RNN reads a new input. And that internal hidden state will be then fed back to the model the next time it reads an input. And frequently, we will want our RNNs to also produce some output at every time step. So we'll have this pattern where it will read an input, update its hidden state, and then produce an output. So then the question is, what is the functional form of this recurrence relation that we're computing? So inside this little green RNN block, we're computing some recurrence relation with a function f. So this function f will depend on some weights w. It will accept the previous hidden state, ht-1, as well as the input at the current state, xt, and this will output the next hidden state, or the updated hidden state that we call ht. And now, then as we read the next input, this new hidden state ht will then just be passed into the same function as we read the next input, xt+1. And now, if we wanted to produce some output at every time step of this network, we might attach some additional fully connected layers that read in this ht at every time step and make that decision based on the hidden state at every time step. And one thing to note is that we use this same function fw and these same weights w at every time step of the computation. So then kind of the simplest functional form that you can imagine is what we call this vanilla recurrent neural network. So here we have the same functional form from the previous slide, where we're taking in our previous hidden state and our current input, and we need to produce the next hidden state. And the kind of simplest thing you might imagine is that we have some weight matrix wxh that we multiply against the input xt, as well as another weight matrix WHH that we multiply against the previous hidden state. So we make these two multiplications against our two states, add them together, and squash them through a tanh, so we get some kind of nonlinearity in the system. You might be wondering why we use a tanh here and not some other type of nonlinearity after all that we've said negative about tanh's in previous lectures. And I think we'll return a little bit to that later on when we talk about more advanced architectures like the Lstm. So then, in addition, in this architecture, if we wanted to produce some yt at every time step, you might have another weight matrix you might have another weight matrix that accepts this hidden state and then transforms it to some y to produce maybe some class score predictions at every time step. And when I think about recurrent neural networks, I kind of think about, you can kind of think of recurrent neural networks in two ways. One is this concept of having a hidden state that feeds back at itself recurrently, but I find that picture a little bit confusing. And sometimes I find it clearer to think about unrolling this computational graph for multiple time steps. And this makes the data flow of the hidden states and the inputs and the outputs and the weights maybe a little bit more clear. So then at the first time step, we'll have some initial hidden state h0. This is usually initialized to zeros for most in most contexts. And then we'll have some input xt. This initial hidden state h0 and our current input xt will go into our fw function. This will produce our next hidden state h1. And then we'll repeat this process when we receive the next input. So now our current h1 and our x1 will go into that same fw to produce our next output h2. And this process will repeat over and over again as we consume all of the input xt's in our sequence of inputs. And now one thing to note is that we can actually make this even more explicit and write the W matrix in our computational graph. And here you can see that we're reusing this same W matrix at every time step of the computation. So now every time we have this little FW block, it's receiving a unique H and a unique X, but all of these blocks are taking the same W. And if you remember, we talked about how gradient flows in backpropagation when you reuse the same node multiple times in a computational graph. Then remember, during the backwards pass, you end up summing the gradients into the W matrix when you're computing d loss dw. So if you kind of think about the backpropagation for this model, then you'll have a separate gradient for W flowing from each of those time steps. And then the final gradient for W will be the sum of all of those individual per time step gradients. We can also write this yt explicitly in this computational graph. So then this output ht at every time step might feed into some other little neural network that can produce a yt, which might be some class scores or something like that at every time step. We can also make the loss more explicit. So in many cases, you might imagine that you have some ground truth label at every time step of your sequence, and then you'll compute some loss, some individual loss at every time step of these output yt's. And this loss will frequently be something like a softmax loss in the case where you have maybe a ground truth label at every time step of the sequence. And now the final loss for this entire training step will be the sum of these individual losses. So now we had a scalar loss at every time step, and we just sum them up to get our final scalar loss at the top of the network. And now if you think about, again, backpropagation through this thing, in order to train the model, we need to compute the gradient of the loss with respect to W. So we'll have loss flowing from that final loss into each of these time steps, and then each of those time steps will compute a local gradient on the weights W, which will all then be sums to give us our final gradient for the weights W. Now, if we have sort of this many-to-one situation where maybe we want to do something like sentiment analysis, then we would typically make that decision based on the final hidden state of this network, because this final hidden state kind of summarizes all of the context from the entire sequence. Also, if we have kind of a one-to-many situation where we want to receive a fixed size input and then produce a variably sized output, then you'll commonly use that fixed size input to initialize somehow the initial hidden state of the model. And now the recurrent network will tick for each cell in the output. And now as you produce your variably sized output, you'll unroll the graph for each element in the output. So then when we talk about these sequence-to-sequence models, where you might do something like machine translation, where you take a variably sized input and a variably sized output, you can think of this as a combination of the many-to-one plus a one-to-many. So we'll kind of proceed in two stages, what we call an encoder and a decoder. So here the encoder will receive the variably sized input, which might be your sentence in English, and then summarize that entire sentence using the final hidden state of the encoder network. And now we're in this many-to-one situation where we've summarized this entire variably sized input in this single vector. And now we have a second decoder network, which is a one-to-many situation, which will input that single vector summarizing the input sentence, and now produce this variably sized output, which might be your sentence in another language. And now in this variably sized output, we might make some predictions at every time step, maybe about what word to use. And you can imagine kind of training this entire thing by unrolling this computational graph, summing the losses at the output sequence, and just performing backpropagation as usual. So as